All right, let's continue with section 7.3, trigonometric substitutions. So these are going to be integrals that fit a particular type of pattern. And when you recognize these patterns, then there are, certain types of moves that can help, right? So this section will help us, recognize when we see an integral that fits this particular mold, and gives us suggestions on how to integrate it. Okay. So the patterns we're going to be focusing on in this section fit something like this. The integral of a giant square root, right? So the square root of some constant squared minus x squared dx, right? So a is a constant, x is the variable of integration. Good. And this is where we're only going to be considering cases where a is some positive value. Okay. So note that if there was an x out in front, even though it looks more complicated, it would actually be simpler to do, right? Because if we had an x out in front here, then we could do an easy u substitution where we get u equal the content of all of this stuff in here, and therefore when we take the derivative, right? So if, let me expand on that over here, if we had the integral of x square root of a squared minus x squared dx, even though it looks more complicated, this x really saves us, because if we do a u substitution where we let u equal to a squared minus x squared, then when we take the derivative with respect to x on both sides, then I end up with du dx equals to minus 2x to the power of 1. So when I solve for du is going to be equal to minus 2x dx. Right? So that really helps us that there's an extra x there. Now if I can just move this around and put it over there, I'd end up with the integral of square root of a squared minus x squared x, and then that dx, and we're almost there. We're just missing this minus 2, which we can just introduce minus 2 right in there, and then balance it out with a minus 1/2 out in here, right? So then we have that the original integral is now equivalent to this integral, and now we have all the components we need, right? So this part is going to become my du, and then in here I'll end up with the square root of u. Good. So this then just simplifies to become negative 1/2 integral of square root of u du, and then the rest is easy. Good. So that extra x out there actually helps if it were there. So if it's not there, such as these cases, even though it initially looks like it should be simpler than that one, it's actually more difficult, right? And those are the ones that we're going to look at in this section. What do we do if we have something that looks like this or similar to something like this? How can we tackle those types of integrals? Okay, so if we change the variable from x to theta by the substitution rule, x equals to a sine theta, then the identity of 1 minus sine squared equals cosine squared allows us to get rid of the root sine, right? And then, of course, this identity comes from our very famous sine squared theta plus cosine squared theta equals to 1, right? So you can solve for either cosine squared or you can solve for sine squared, and that's where this guy comes from. Good. Okay, so the suggestion, just sort of out of the blue, is that when we have something like this, the suggestion is going to be to replace the x with a sine theta, right, where a is the constant. When we replace the x with a sine theta, we get a squared sine squared. We can factor out the a squared, right? Then we end up with 1 minus sine squared theta. We can then use this property to rewrite this part as cosine squared. And then we can take the square root of a squared, that's going to be a, and here this becomes the absolute value of cosine theta. The reason this becomes a is because from the beginning we assumed that a had to be positive. So some positive number squared, and then we take the square root of it, brings you right back to a. Whereas here, it isn't yet totally clear that cosine is only going to be a positive value, right? Cosine of theta could be a negative. But if we take something and we square it, right, some value and we square it, and then we take the square root of it, this is by definition the absolute value of something, right? Think about it. If the input value in here, if we input a positive number, say a positive 3, and we square it, we get to 9. We square root it, the output is going to be, right, it's going to output a positive 3. Good. And if we input a negative 3 in there, and then we square it, we get to positive 9, and then we square root it, that's going to bring us right back to positive 3, right? So whether it's positive 3 or negative 3 at the start, at the input, when we output it, it outputs us to positive 3 always, right? So that behaves in the same way that we know this does. If I input a positive 3, the output is positive 3. If I input a negative 3, the output is also positive 3, right? So whether you input a positive or a negative value, the output is always the positive one. So therefore, these two operations behave the same way. Good. So the square root of cosine squared theta is the absolute value of theta. The only way we would be able to remove those absolute values is if we, for some reason, knew that cosine was always positive. Okay. So let's notice the difference between substitution rule, where the rule would be that u equals to a squared minus x squared, in which the new variable is a function of the old one, and the substitution of x equals to a sine theta. The old variable is a function of the new one, right? So for example, let's say I had an integral that involved this kind of statement. Like let's say, for example, it was a squared minus x squared sine of a squared minus x squared. Say I wanted to integrate something like this, dx. Okay, so one idea could be to let a u substitution, u equal to a squared minus x squared, go in here. But as we saw before, when I take the derivative with respect to x, I'm going to end up with negative 2x. Right? So du is going to be equal to negative 2x dx. And, well, I have the dx, but I'm missing the minus 2x. Now, I can always throw in a constant to balance that out like I did before, minus 2, and then I can balance it out with a minus 1/2. But what you're not allowed to do is to throw in an extra variable, right? The variable of integration, x. We can't just throw in an x here and balance it out here. That doesn't work. That only works for constants. So we're out of luck here, right? Only if the original question happened to have an extra x in there would this work out, right? So when you're doing a u substitution, it's only going to work if you're able to substitute the whole thing, right? If there was an extra x, then that would work out well. I'd end up with the square root of u, sine of u, du, and that would be simpler. But here we're a little out of luck. Good. On the other hand, if I'm facing the exact same question, the integral of a squared minus x squared sine of a squared minus x squared dx. Good. Okay, so the idea is I'm going to let x equal to a sine of some new variable theta. Okay, so then I can substitute it in there and get some interesting, hopefully something useful out of it. But note that when I take a derivative with respect to theta, d theta, derivative with respect to theta of this side, d theta on the other side, a sine of theta, then on the left-hand side, I just end up with dx d theta. And on this side, well, I end up with a cosine of theta. Good. So then my dx is equal to a cosine of theta d theta. Good, 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 good. Okay, so my dx is already right here. So this would be replaced by the a cosine of theta d theta. Right? Did you guys catch that? Hopefully you caught that subtle sort of difference. Let me point that out one more time if I can zoom out a little bit. Come on. So let's point out that subtle difference here. Here, if I do a standard u substitution, u equals to this, I take the derivative, the du ends up in the numerator, which means I move the dx to the other side. And so now I'm crossing my fingers that this whole thing over here appears in my integral somewhere so that I can do a substitution and end up with a du. Right? I'm hoping that this will end with something that looks like this, the integral of square root of u sine of u. That's my hope when I'm doing this substitution, sine of u, du, du. Right? So I'm hoping that this du appears somewhere in there, and right now we're out of luck because it doesn't have the x, so I'm not able to do that, and it's now my u substitution is ruined. On the other hand, when I do this, when I let x equal to a function of a new variable theta, when I take the derivative, the dx ends up in the numerator. See how down here, up here it ended up in the denominator? Here the dx ends up in the numerator, which means that I just multiply whatever, as long as that derivative exists, multiply the d theta to the other side, and now my dx is guaranteed to be there, right? I don't have to cross my fingers and hope that it's somewhere in there or anything. It's just dx by itself, right? Unobscured, equal to some function that doesn't have x's. Good, 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 good. If you're wondering over here, well, why didn't you just divide this side and you can solve for dx? Well, that's fine. You could solve for dx, but you would end up with a function that also has an x in it, right? You'd end up with du divided by negative 2x, and you'd still be in trouble. Well, not really trouble, but that just makes the whole thing more complicated, right? We'll look at examples at some point where that is the trick you have to do. So, anyway, good, 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 good. So for now, this means that this helps us out immensely. The dx is always, we don't have to wait for it to be there. It'll be there. So if this can simplify into something we can integrate, then good, right? It'll be helpful. All right, so hopefully that made a little sense. Let's go back over here. So if we replace u by x and x by t in the substitution rule, we end up with this, right? So we have an original integral, which is some function of x dx. We're going to let x equal to some function of t, which means that my dx dt is going to be equal to g prime of t, some function, the derivative of this g function, assuming it exists. Therefore, my dx is going to be equal to g prime of t times dt. Good? So my dx becomes g prime t dt. In here, this is my former value of x, right? So I end up with f of x times, and then my dx becomes g prime of t dt. Okay. All right, so in order for this to work out, we got to make sure that the substitution we create is one-to-one, right? So that's really important for us to make sure that this substitution is one-to-one. And remember that the sine function is not one-to-one if we consider the whole thing. So here, just as a rough drawing of it, the sine function starts there, comes up there, comes back down here, goes back down that way, right? And it repeats itself back here, comes back, whoa, that was ugly. Comes back down here and goes up that way and goes like that. Good, good, good. Okay, so in order for us to fudge this into a function that is one-to-one, remember that a one-to-one function, here, let's go, this goes from 1, and then this guy over here is -1, like that. A one-to-one function means that you can go forwards and backwards with it. So if we have some value a that maps to this value, some sign of a value there, sign of a, some output value there, that means that we can also go forwards with it. If we start here, we can trace it back to there, and this traces back to there, and this traces back to there. So that's a one-to-one function. So going in this direction, if we start with this input, then yep, it traces to exactly one unique value, and that's our output. But when you want to go backwards, this traces back to this one, but it also traces back to that one, and it also traces back to that one, right? And then there's going to be another one over there, and another one over there, and another one over there, right? So there's an infinite number of values that this will return from. Good. So the way we get around that is to restrict the domain of the sine function. If we only focus, right, from -pi/2 to +pi/2, if we restrict the domain of the sine function to just this little zone from here to there, in this little zone, the sine function is one-to-one. Every single angle from -pi/2 to +pi/2 can be traced to one unique decimal value from -1 to +1. And the reverse is also true. Every single decimal value from -1 to 1 can be traced back to a unique angle between -pi/2 to +pi/2. Okay, so when we make this substitution, we also make that restriction. Theta is got to be some angle between -pi/2 to +pi/2. That guarantees that it's going to be a one-to-one function. Good. So out of the entire sine graph, we're only going to be focusing on this little part from there to there for the sine function. For similar reasons, the cosine function is also restricted, and so is the tangent function. So the book provides you with this little table here so that we can be clear on how to restrict our domains and the suggestion. So if we have an integral that involves something that looks like this, a square root of a constant squared minus x squared, the suggestion is that we use a equals to sine theta, where theta is restricted between -pi/2 to +pi/2. That'll guarantee that it's one-to-one. And the suggestion is that this will be helpful in trying to integrate, calculate integrals that involve this expression. Good. If we have integrals that involve this expression, some constant squared plus x squared, the suggestion is that we let x equal to a tangent of theta, where again the tangent of theta is restricted by the exact same domain. Remember that the rough, very, very rough graph for the tangent function would look like this. Kind of comes this way, kind of goes that way, and there are vertical asymptotes that go this way and this way at -pi/2, oops, sorry, not negative, +pi/2 and -pi/2. Good? Good. And that's what this is. That's where this is an angle theta, and I should have put that over here. I don't know why I put it way up there. So this is -pi/2 right in there, and this is +pi/2. Good. Okay, so the tangent function is going to experience all real numbers from -infinity to +infinity throughout the angles that extend between -pi/2 to +pi/2. Good, so that's how we restrict that. And then if you think about the cosecant of theta function, just draw the cosine function and then draw the 1 over cosine, which means we invert it. And then again, let's do a rough sketch of that. So very, very rough. The cosine function does this thing, comes back up and goes like that. And then again, it does the same thing over here and goes back up and goes back that way. Good. So that's cosine of theta. And secant of theta is equal to 1 over cosine of theta. So if we think about where this function goes, well, there at 1 over 1 is 1. And then as it approaches 0, as it gets smaller and smaller and smaller, the denominator gets smaller and smaller, the whole output gets bigger and bigger and bigger. And then there's going to be an asymptote right there at 0. So an asymptote there, an asymptote there. Right, so this goes this way, this goes this way. And then over here, there's also going to be an asymptote there, and an asymptote there. Right, so in green, let me just draw what these things look like. They go that way. They go this way, and then over here they go this way and they go that way. Wow, this is really ugly, but you get the idea. Go that way, they go that way. Okay, now that I've completely butchered it, let's just really quickly get a more professional look at these graphs. Let's go to Desmos, desmos.com. So we can do y equals to sine of x, and there we go, that's the sine function, right? And if we do something like y equals to 0.5, for instance, right? So we know that sine of pi over 6, sine of 30 degrees, is equal to 0.5. But if we want to go backwards, what is the angle such that sine of that angle equals to 0.5? Well, there's lots of angles. There's this one, but there's also that 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 one, right? So there's an infinite number of angles such that sine of that angle equals to 0.5. That's why we restrict our domain to go from x equals to pi over 2 and x equals to negative pi divided by 2. Let's put it in blue. Done. Okay, so if we just restrict the sine function to just this little piece, in that little piece, the sine function is going to be 1 to 1. Good. Okay, the other one was tangent. So tangent looks like that, right? And then there's these vertical asymptotes that are not being drawn here, but there are vertical asymptotes there, and then over here and over there, right? So remember, sine over cosine equals to tangent. So whenever cosine is equal to 0, we have a vertical asymptote. Okay, all right, so then we can restrict our tangent function, which is all of these red ones. We can restrict it to just the section between negative pi over 2 to positive pi over 2, and we see that we have one section of the tangent function that is 1 to 1. Good, so that's functional there. And then next we also have secant. We're going to work with secant x. All right, so secant x looks like that. And again, that comes from looking at our y equals cosine. Oops, cosine x. Right, so here is the cosine function. And then whenever cosine equals to 0, we're going to have vertical asymptotes. So cosine equals to 0 there at pi over 2. Cosine equals to 0 there at pi over 2. And whenever cosine equals to 1, secant, which is 1 over cosine, is going to also equal to 1. So there, and there, and there, and there. Right, so all of these red ones are the graphs of secant x. So now the trick is to partition it in a way that gives us a 1 to 1 function. So what the author suggests is that we restrict it from 0 to pi over 2, and that gives us this little segment over here. So from 0 to pi over 2, we can do a perfect one-to-one matching between all of those angles between 0 and pi over 2 and all of the output values that are 1 up to positive infinity, inclusive of 1. Right? So this little segment here. Good. And then the other one is to begin at pi, and extend it out to 3 pi over 2. So this little segment would capture all the one-to-one functions between all the angles between pi and 3 pi over 2, all of these angles, and this segment over here, which would be all the output values starting at -1 down to -infinity. Okay, hopefully that clarified things. So having said that, let me just highlight that here. Right, so the one-to-one function then is going to be just, let's put it in purple. It's going to take my secant graph, and it's going to take that part of it, and it's going to come over here and just take that part of it. Okay, so from 0 through pi over 2, from 0 to pi over 2, and then from pi to 3 pi over 2. So from pi to 3 pi over 2. So this little segment right in there, and then this little segment right in there. If we restrict our theta values to be values in this section or this section, we will have a one-to-one function. Okay, so that's where this table comes from. We need to make sure that we have one-to-one functions by restricting the values of theta, and then we just have to kind of pay attention to these suggestions. Once we see a couple of them in action, you'll see why they work, and we'll also use these identities as part of the solution, as part of the solutions. Good. Okay, so let's begin with an example. So let's say we want to integrate this guy here. Okay, so we have 9 minus x squared. So let's work on that off to the side for a little while first. So we have the integral of 9 minus x squared. We can rewrite this as 3 squared minus x squared. And then based on the suggestion, we know that we should try let x equal to 3 sine of theta. Right? That was just the suggestion. A squared minus x squared, let x equal to a sine of theta. So why does that help? Okay, so now let's go back over here. So we have 9 and then minus, and instead of just an x, now I'm going to let this be 3 sine of theta squared. Right, instead of x, from there, instead of x. And now we just simplify that, and we end up with 9 minus 9 sine squared theta, square root of that whole thing, which equals to 9, 1 minus sine squared theta, square root of that whole thing. Good. Then we can separate this into the square root of 9 times the square root of this, and we can use our Pythagorean substitution to replace it like that. And then something squared square rooted, as we covered before, that must mean that this is the absolute value of cosine of theta. Good. Okay, now let's add a little extra layer here. Back when we let this be our substitution, as we just said, we need to restrict this. We need to make sure that theta is, a sine of theta is 1-to-1, which means that we're restricting theta to be between negative pi over 2 and positive pi over 2. Right? So we put a restriction on the values of theta. So now if you think about cosine of theta, where theta is restricted to these values, in this section, right? This is spanning quadrant 1 and quadrant 4, right? If we think about the angles, from 0 to there, that's from 0 to pi over 2, and then negative would go counterclockwise, well, would go clockwise, sorry. So if we go this way like this, we can go negative pi over 2. So we're covering everything in this side, quadrant 1, Q1, and Q4. And cosine of any angle in this region, cosine is always going to be positive. Good. So I don't need these for this. For theta, always being greater than or equal to negative pi over 2 less than or equal to pi over 2, for that section, the absolute values are not needed. So this just becomes 3 cosine of theta. Good, 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 good. Okay, so that's what this whole thing reduces to. Good, 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 good. Now we have to think about the derivative of this. So we have that x is equal to 3 sine of theta. So d theta of the x is equal to d theta of the 3 sine of theta, which means that dx is equal to 3 cosine of theta. Derivative sine is cosine. Oops, this is theta. So dx is equal to 3 cosine of theta d theta. So I'll need that for my substitution. I'll need that right there. So those two pieces can help me come back over here and replace this whole thing over here. Okay, so this whole integral then is going to be equal to the integral of cosine, 3 cosine of theta, 3 cosine of theta. Good. That's how we got this whole thing, 9, all right, so that's in the numerator. That gives you that. Divided by, and then x, which we said is this thing, so that's going to be 3 sine of theta squared. And then the dx, which we said is equal to 3 cosine theta d theta. 3 cosine theta d theta. Good, 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 good. Okay, so this will simplify a little bit. This 3 cancels with, oh, wait a minute, no, sorry, see, I made a mistake here. Let me rewrite that right in here. This is 3 sine of theta, and then the whole thing gets squared, not just the sine. Good. And I have 3 times 3, and I have 3 squared, so I know that's going to cancel. I end up with 9 cosine squared d theta divided by 9 sine squared theta. Integral of those two. Okay, so the 9's cancel, and I end up with the integral of cosine squared over sine squared, that's cotangent. Cotangent squared theta d theta is what I want to integrate. And that's one of our known integrals. You remember it. Or we can separate this, so we can use our property that cotangent, so use that cotangent of theta squared plus 1 equals to cosecant squared theta. So we can replace cotangent squared is equal to cosecant squared minus 1. We can replace that integral of cosecant squared theta, and I'm terrible here, there's a theta there, and a theta there, theta there, theta there, getting really messy, minus 1 d theta which can then be separated into two separate integrals. The integral of cosecant squared theta d theta minus the integral of 1 d theta. And something whose derivative is cosecant squared is equal to cotangent. Cotangent of theta, its derivative is, well, close to that. It's going to be negative, so we have to throw in an extra minus. Minus, and then this is going to be theta. And then there's a constant in there. Good, 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 good. Okay, we're almost done, except that the original question was given to us in terms of the variable x, not the variable theta. So we have to go back to retranslate our statement, our final response here, in terms of the variable x. Let me zoom out a little bit more to capture some of this. So now, using that we let x equal to 3 sine of theta, we can divide both sides by 3 and move it around, and I end up with sine of theta equals to x over 3. So if I create a nice little triangle here, here is theta. Theta is equal to opposite over hypotenuse, so that would be x 3, and there's a missing side here, call it a. So a squared plus x squared equals to 3 squared. So a squared is equal to 9 minus x squared, or a equals to the square root of 9 minus x squared. Right, so that's what this is. This is equal to square root of 9 minus x squared. Okay, so based on this little triangle, I'm able to solve for this. Cotangent is equal to adjacent over opposite. So this is going to be equal to minus square root of 9 minus x squared over opposite, which was x. Theta can be solved from here. Right? Theta is equal to sine inverse. Theta equals to sine inverse of x over 3. So this is going to be minus sine inverse plus some constant. Good, 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 good. Questions? Okay, so hopefully that's clear enough. Okay, so as a recap, we saw that we had a constant minus x squared, and then based on the suggestion by the author, this would be a great case to let x equal to 3 because of the 9. 3 squared is 9. 3 sine theta. Its derivative is going to end up being dx equals to 3 cosine theta d theta. So make sure we include the derivative dx into there. When we simplify that root, that square root, we end up with 3 cosine of theta. So that's where this comes from. This is that root becomes 3 cosine of theta. This comes from the dx part of it. And then we have this other denominator part here where we have an x squared, which becomes 9 sine squared theta. Things work out, get to this guy. We use one of our trigonometric identities to rewrite it this way. And then this is a straightforward integral now. All right, hopefully that worked out well. Let's see what the author did. Probably, hopefully, similar things. 3 sine theta. Okay, so we still get that this part of it simplifies to 3 cosine of theta. Replacing all of it, we get to the same thing, cotangent of theta. Replacing that guy gives you this. Good, 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 good. And then a triangle, same as what I did. And then we can replace each part of it and end up with the same answer I got. All right, let's move on to another example. Find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals to 1. Okay, so this is a case, note that this is where the a and the b are constants, right? So this, for example, could be a case, for example, this could be something where we have x squared over 9 plus y squared over 4 equals to 1. Or it could be x squared over 16 plus y squared over 25 equals to 1. And of course, they don't have to be whole number constants, but that just makes it easy to do. So just to visualize what these looks like, let's go back to Desmos. Let's get rid of these things. Let's rid of these things. Okay, so let's just type in our equations. So we have x to the power of, x power of 2, and the whole thing gets divided by, say, 9, plus, and then we have y to the power of 2, and then the whole thing gets divided by, say, 4, 9 and 4. Okay, and then we set that equal to 1, and that's what we get. Right, we get an ellipse that looks like this, right? It's kind of this oval thing like this. And note that in the y-axis, this y squared was divided by 4, and then here we end up with this, right? As the y-intercept points, 0, 2 and 0, -2, right? Connected, associated with that 4. And then in the x-axis direction, we get x-intercepts of -3 and +3, like this, and then of course they are associated with that 9 right there. Good. So then if we switch it around, but if we change those constants to the denominator, like let's say instead of 9 there was a 16, and instead of 4 there was a 25, then we get something like that. Let's change the color. How about we make it green? Right, so now this oval looking thing in green is this equation, and now the y-axis is associated with +5 and -5, and the x-axis is associated with -4 and +4. Good, so that's associated with this constant in the denominator. Good. Okay, so now if we let's say we make this a slider A, and we make this a slider B, make those two sliders, and then raise this to the power of 2, and raise this to the power of 2. Now I have something that can, let's pause that. Now I have something that can be used to create, right, various ellipses based on the constant that goes down there. Here's where a 4 is written, here's where 3 is written, so here's a 2.9, right? So here's different values of the A, and then at the same time I can have, let's stick to positives, I can have different values of the B. Okay, so no matter what the values are, whatever they are, the area of the whole thing, we're going to take a little shortcut. We're going to say that this is symmetric, right? We can break this up into 4 equal quadrants. So what we want to do is just find the area of one of these little quadrants. Good. And then if we multiply it by 4, we'll get the area of the entire thing. Good. Okay, so let's begin by solving for y squared. So let's go back over here. If we solve for y squared, we end up with y squared over b squared is equal to 1 minus x squared over a squared. Getting a common denominator of a over a squared over a squared, we end up with a squared minus x squared all over a squared equals to y squared over b squared. Good. So if I multiply both sides by b squared, I end up with y squared equals to b squared over a squared times a squared minus x squared. And if I take the square root of both sides, I end up with plus or minus the square root of b squared over a squared, which is just going to be b over a. Good. And the square root of a squared minus x squared. Okay? So in terms of functions, the positive is going to end up being the top part of it, right? As we saw, this is going to be some sort of an ellipse, and just for the sake of argument, let's say that it, whoa, that's really ugly. Let's say that it looks like this. Well, only prettier. Something like that. This is going to be y, this is going to be x, and we know that it's going to be a value there, which is associated with the value here, a. Right? So this is going to be equal to a comma 0, whereas this one is going to be equal to negative a comma 0. Okay. And then over here, these ones are associated with the constant underneath the y variable. So this one is going to be equal to 0 comma b, whereas this one is going to be equal to 0 comma negative b. Good. So to find the area of the entire thing, we're going to focus on just finding the area of this guy and then multiplying it by 4, and that'll give us the area of the entire thing. Good. Okay, now when I solve for y, the plus part of it as a function is the top half of the ellipse, whereas the minus part ends up being this bottom part down here. Good. So this part of the ellipse up here as a function, just the top half is y equals to positive b over a square root of a squared minus x squared. Good. And then just the bottom part, just focusing on this part over here, this bottom part as a function is y equals to negative b over a square root of a squared minus x squared. Good. Okay, so what we want to do to find the area is just integrate from the variable starting at 0, ending at a, of the function, this function, right? And that'll give us this area in red. So area, red area, I'll put red area is equal to the integral as x ranges from 0 to x ranges to a, right? X will range from 0 all the way to a, and we want to integrate this function, which will be b over a square root of a squared minus x squared dx. Good, so that'll be that area. But of course we want the entire ellipse, so we're going to have to multiply this area times 4 to get the entire area. Good, so now let's put that total area. Zoom that over here a little bit. So therefore the area of the total ellipse, the total area I'll just put, total area is going to be equal to 4 times that. 4 times the integral as x ranges from 0 to x ranges to a of b over a square root of a squared minus x squared dx. Good, good, good. Okay, so let's work on this guy. So hopefully it's clear enough where this integral comes from. Okay, so now based on our suggestion, we're going to do the same thing. We're going to let x equal to a sine of theta, which means that my dx d theta is going to be equal to a cosine of theta, which means that dx will be equal to a cosine of theta d theta. Good. And now let's take this thing and simplify it off to the side here. We have a squared minus sine, oops, not sine, minus x squared, which is then going to be a squared minus a sine of theta squared, square root of the whole thing, which will become a squared 1 minus sine squared theta all over 1 root. Okay, so then this becomes this squared times the square root of 1 minus sine squared theta, which then becomes a times the square root of cosine squared theta, which then becomes a absolute value of cosine of theta. And just like before, we have to also throw in that theta is limited. Pi over 2, right? In order to make this 1-to-1, in order for this to be a 1-to-1 function. So this is just going to become a cosine of theta, right? Cosine of theta in this region is always positive, so we just don't need the absolute values, right? They're not needed. Cosine of theta is always going to be positive as long as theta is in this range. Good. Okay, so now we're ready to substitute. We got, well, b and a are just constants, right? There's no need to have those there. I can just pull them out. So let's put it over here and say that this whole thing is equal to 4 times b divided by a, integral of, and then x equals to 0, x equals to a, and then I have the square root of, this whole thing just turned into a cosine of theta, a cosine of theta, and then my dx is this guy, another a cosine of theta d theta. Good. I have two a's, one of them can cancel with this guy, and then I'll have one more remaining, which I'm going to pull out in front, and then I'll have the integral of cosine theta squared d theta. But notice that the limits of integration up here were for the variable x, right? So I'm going to have to either change my limits of integration now so that they match, so that when I try and solve it, I already have the corresponding limits of integration, or I can find the antiderivative in terms of theta and then go through the trouble of re-expressing that function in terms of x so that I can plug in the correct x values. Hopefully that made sense. Okay, so let's simplify this a little bit. So when x equals to a, remember here is our substitution, we're going to end up with a equals to a sine of theta, right? So using this, if the x is an a, the output is an a, that must mean that sine of theta is 1, right? So divide both sides by a, divide both sides by a. So we get that 1 equals to sine of theta. Now when does sine of theta equal to 1? Well, that's going to be at pi over 2. Good. Okay, and then the other one we have is that x equals to 0. When x equals to 0, we end up with 0 equals to a sine of theta, where a is some constant. So we divide both sides by a, we still get that 0 must be equal to sine of theta. And when the sine of theta equal to 0, that's when theta equals to 0. Okay, so we have our new limits of integration that match up with our theta. And we're ready to re-express this whole thing in terms of theta. This is going to be equal to 4ba, I'm just pulling out one of those a's out there, integral of, and then I'll have cosine squared theta d theta, And this is where theta ranges from 0 up to theta goes up to pi over 2. Good, so now everything matches. And in order to integrate this, we're going to use our power reduction formula, right? So using the fact that cosine squared theta is equal to 1 plus cosine of 2 theta over 2. We're going to use this as one of our trigonometric identities to replace that, and then that'll help us find the integral of it. Okay, so this will become 4BA integral of theta goes from 0 through theta goes to pi over 2, and this becomes 1/2 1 plus cosine of 2 theta d theta. I can factor out that half and get a 2b theta, BA integral as theta goes from 0 to theta goes to pi over 2 of 1 plus cosine 2 theta, and then the whole thing d theta. Good. Okay, so let's squeeze that over here. This is then equal to 2BA, and then we're going to end up with a theta from here. Right? The antiderivative of 1 is theta. And then from here, it has something to do with a sine 2 theta. Right? The derivative of sine 2 theta is cosine 2 theta, except that we'd have to do that chain rule and end up with an extra 2, which we don't want because it's not on there. So we're going to have to toss in a 1/2 out there. Okay? And all of that gets evaluated as theta ranges from 0, theta goes up to pi over 2. Good. Okay, so then this becomes 2BA parentheses. Okay, so then we put in that pi over 2 plus 1/2 sine of 2 times pi over 2 minus, and put a big parentheses here. Let's put parentheses here for the case where we plug in pi over 2 and pi over 2, minus, and then parentheses where we put theta equals to 0. So it would be 0 plus 1/2 sine of 2 times 0, and then we simplify that. Okay, so that'll be 2BA, and then that's just pi over 2. These 2's cancel, and I end up with sine of pi, and sine of pi is 0, so this whole thing is just going to turn out to be 0. Okay. And sine of 0 is 0, so this whole thing ends up being 0. So this whole thing just kind of evaporates into just being 2AB times pi over 2 times pi over 2. The 2's cancel. And so my final result is just going to be pi times BA. Good. Good. Let's see if we can get a bigger sense of this whole thing. This was ugly. Big problem. Okay, that's as good as it gets, I think. Alright, so we had an ellipse. We wanted to find the area of the whole thing. We figured out how to express one quadrant of it. That would be this part here, and then we multiply by 4 to get the area of the entire thing. And it turns out to be a pretty nice little formula. It's just pi times BA. Notice that the B and the A correspond to these points there. So in the case, so for example, then if I had x squared over 16 plus y squared over 9 equals 1, then I want to know the area of this whole thing. Okay, so I know that this is going to be an ellipse that looks a little like this, only not so ugly. But, okay, so we know it's going to be an ellipse like this. We know that this goes out to 4, 0. We know that this goes out to negative 4, 0. We know that this goes up to 0, 3. We know that this goes down to 0, negative 3. And then the area of the entire thing is going to be actually pretty easy. It's going to be pi times 3 times 4, which is 12 pi. The area of the entire thing is 12 pi. So it's like a really nice formula for the area of any ellipse. Good. And if you think about a case where, in fact, these two numbers are the same, if these two numbers are the same, then that means I can simplify it this way. For example, if I had x squared over 16 plus y squared over 16, so they're both the same, equals 1, then that would actually be a circle, like this. Both the x and the y would be associated with the same thing. This would go out to 4, 0. This would go over to negative 4, 0. This would go up to 0, 4. This would go down to negative 0, negative 4. Right? It would be a nice perfect circle, which would mean that this is a circle with radius r equal to 4. Right? So this becomes a circle. We can also multiply both sides by 16 and end up with x squared plus y squared equals to 16, which is the general formula for a circle centered at the origin, centered at 0, 0. Good. And so what's the area of this whole circle? Well, according to our little formula, it's going to be equal to pi times the 4 from here, times 4, times, well, this one also had a 4 in this case, so 4 times 4. So the area is going to be 16 pi, which also happens to be the same thing as r squared, right? So remember that the area of a circle is also known as pi r squared. And so we've confirmed for when the case of A equals B, which is equal to R, right? In cases where the A and the B are the same, which therefore means that they equal the R, then the formula of pi times A times B is the same thing as the formula r squared pi, right? So we've confirmed that the area of a circle is pi r squared. That's pretty cool. Cool. Okay, that was a whole lot. Let's capture some of it. Okay, let's see what the author did there. Okay, it looks like the author did the same thing, worked with that formula, solve for y, we get a plus or minus. It's the top half of the ellipse will be the positive end. Good. So that quadrant is 1/4 of the whole area. Okay, so same thing. Yeah, use the same guy. Pi AB, and then for a circle, we end up confirming that pi r squared is the same thing. Cool. All right, so another example. find this integral, x squared times the square root of x squared plus 4, where x plus 4 things in the denominator. Okay, so as per their suggestions, we're going to let x equal to 2 tangent of theta. 2 tangent of theta. Good. So therefore, its derivative, d theta, dx d theta, is going to be equal to 2 secant squared theta. So dx is equal to 2 secant squared theta d theta. Good. So we'll need that when we substitute it. And then the x is going to be that guy, so this is going to be squared. We just have to figure out what this is. So let's simplify that. We have the square root of x squared plus 4. And then after we do our substitution, we get 2 tangent 2 tangent of theta squared plus 4. All of that gets square rooted. Gives us 4 tangent of theta squared plus 4. All of that gets square rooted, which then gets us to square root of 4 times the square root of tangent squared plus 1, which is equal to secant squared. So this is going to be 2 times the square root of secant squared theta. Good. And then again, we go back to our restrictions. So in our restrictions, we had that theta. This is for negative pi over 2 less than or equal to theta less than or equal to pi over 2. That's what guarantees that this is 1 to 1. And now if we're only letting cosine be a value between negative pi over 2 to positive pi over 2, that's going to guarantee we have a positive answer. So therefore, 1 over cosine is always going to be a positive answer as well. So we can just say that this is the same thing as 2 absolute value of secant of theta, which then just gives you 2 secant theta. Okay, so we have all the makings, everything we need to do a substitution here. So let's do it. So this is going to be equivalent to the integral of, and then we have a giant fraction where the x squared is going to be 2 tangent of theta squared, and the square root of x squared plus 4 turns out to be this thing, so times 2 secant of theta, there's a 1 there, and the dx is this, so times 2 secant squared theta d theta. Good. Okay, so some things simplify a little bit. So we have a 2 here, and we have a 2 there, and we have a secant theta, and we have a secant theta squared, so we can get rid of the squared, we can simplify that. So we still have the following, so this equals that, and then this, there will still be a 4, so it'll be a 1/4 out here, and then a tangent squared in the denominator and a secant in the numerator, secant of theta in the numerator, and then tangent of theta squared in the denominator, d theta. Good. Okay, so let's simplify that by converting all into sines and cosines. So this is going to be 1/4 integral of 1 over cosine of theta, that's that secant, divided by, and then this is going to be sine squared theta divided by cosine squared theta, d theta. Right? So here's secant theta, here's tangent of theta. So the numerator times the reciprocal of the denominator means that this will simplify into the integral of 1 over cosine theta times cosine squared theta over sine squared theta. d theta. And now this guy cancels with that, just one of them. And so what survives is something a little simpler, 1/4 the integral of cosine of theta all over sine squared theta d theta. Good. Okay, so now we're going to do one more substitution. Let's let u equal to sine of theta. Therefore, du d theta is going to be equal to cosine of theta. And so du will be equal to cosine of theta d theta. Right? So we have our du right there, and then this turns into 1 over u squared. Okay, so let's put that over there. So this then becomes 1/4 the integral of 1 over u squared, that's 1 over sine squared, right? 1 over u squared, times du. Good. Okay, so this can be also written as 1 over 4 integral of u to the negative 2 du. Which is just going to be equal to 1/4 1 over u, which is a little minus out in front. So, you know what, let me stick to the same notation. This is going to be u to the negative 1. The derivative of this means you bring down that negative 1 and you subtract 1 from the exponent. That gives you that guy. So in order not to have that minus, we have to introduce an extra minus. Good. So this becomes this, plus a constant. So this becomes negative 1/4 times 1 over u, plus a constant, where u is sine of theta. So this becomes negative 1/4 times 1 over sine of theta plus c. And 1 over sine of theta is the same thing as negative 1/4 cosecant theta plus a constant. Almost there. Now we got to go back to the original substitution. I got off track here. So let's go back way over here. So we have that negative 1/4 cosecant theta plus c. But now, going back to the expression of x was equal to 2 tangent of theta, which means x over 2 equals tangent of theta. If we create a nice little triangle of that, we get theta is this. Tangent is opposite over adjacent, so this is x over 2, and there's a missing value h. So 2 squared plus x squared must be equal to h squared. So square root of 4 plus x squared equals to h. Right, so that's what this was. Square root of 4 plus x squared. Okay, so sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. So this would be negative 1/4 times 4 plus x squared, square root of that whole thing, all over x plus some constant. Good. Okay, that was fun. Let me box that guy up. Let's see what else we got. Let's see if the author did the same thing I did. minus x squared plus 4 over 4x. Uh-oh, did I mess up somewhere? I think I missed the 4 somewhere? Over 4x. No, that's fine. So 4x plus a constant. Yep, same thing. All right, let's look at another one. So, very similar to the other ones. This is again a case where we have the square root of x squared minus a squared, and per their suggestion, the author's suggestion, when we have something like this, they suggest that we let x equal to the a secant theta. Okay, so if this is the x, that means that dx d theta equals to derivatives secant is going to be secant tangent, so this is going to be a secant theta tangent of theta. So dx is equal to a secant theta tangent of theta d theta. So that'll be my substitution for the dx. Now let's see how this root simplifies. If we end up with x squared minus a squared, and we have the square root of that whole thing. So this ends up being a secant theta, the whole thing gets squared, minus a squared, that thing gets square rooted, which ends up being a squared secant squared theta minus a squared, square root of that whole thing, which gives you the a squared square rooted times, and then we have the square root of secant squared theta minus 1. And secant squared theta minus 1 is just going to be tangent of theta, as per one of our trig identities. Tangent squared theta. Good. Now again, we got to confirm our restrictions here. So secant theta is going to be restricted to be secant theta is going to be restricted to be between 0 and theta and pi over 2, and or it jumps again, it's trapped between pi and 3 pi over 2. Okay, so this is going to be quadrant 1, or quadrant 3. Okay. And in quadrant 1, tangent is definitely always positive. Tangent of theta is going to be positive in quadrant 1, and it will also be equal to positive values in quadrant 3. Tangent of theta is also positive in quadrant 3, right? Because remember, tangent is sine over cosine, and in quadrant 1, both sine and cosine are both positives, so that's going to be positive. And in quadrant 3, both the cosine and the sine are both negatives, so negative over negative makes a positive, so tangent of theta is also positive in quadrant 3. That guarantees that this is going to simplify into a absolute value of tangent of theta, but then the absolute values are not necessary, since in these regions, for these values of theta, this part is always positive, so we can just say that it's equal to tangent of theta. Okay, so we have everything we need to come back over here and replace this. So we have that integral is equal to, and then the denominator is just going to be a tangent of theta, 1, times the dx, which is equal to a secant of theta tangent of theta d theta, okay, which simplifies a little bit since the a and this a cancel, tangent of theta and tangent of theta cancel, so we're left with just secant theta. Integral of secant theta d theta. Now that's one of our standard integrals to just kind of memorize. Or if you remember, there's a little trick for finding this integral. I don't know, you either remember the little trick or you remember the actual solution. Either way, you got to do a little memorizing. And the little trick for this guy is to multiply this by a new version of 1. Right? We love that trick in math. Find a new version of 1. The perfect version that will be helpful. And that will, in this case, be equal to secant theta plus tangent of theta divided by secant of theta plus tangent of theta. Right? So if we multiply that whole thing, secant of theta times that, and we have the same integral times d theta. Good. Distributing it, we end up with the integral of secant squared theta plus secant of theta times tangent of theta divided by the denominator, which is secant theta plus tangent of theta d theta. Good. And now we're going to let u equal to this denominator. Let u equal to the denominator, secant of theta plus tangent of theta. So du d theta is equal to the derivative of, well, I'll just do it this way, d theta of secant theta plus tangent of theta. So du d theta is equal to the derivative of secant theta, which is equal to secant theta tangent of theta, plus the derivative of tangent of theta, which is equal to secant squared theta. So my du is equal to secant theta tangent of theta plus secant squared theta d theta. That whole thing as a d theta. Okay, well, that's actually exactly the numerator. Secant squared theta plus secant theta tangent theta times theta is exactly du. Okay, I'm going to circle it all. This whole thing times the d theta, all of this is my du. Good. So now I'm ready to replace this. Do my substitution here. Put it up here. So this integral now becomes the integral of 1 over u times du, which then becomes ln of u plus a constant. Good. And the u was this thing. Becomes ln of absolute value of secant theta plus tangent of theta, absolute value, plus a constant. So if you remembered it from here, right, so it's perfectly okay to go from here and go, oh, okay, I memorized it, I remember it, and then you just go from there to there. Or if you don't remember that, maybe you'll hopefully remember at least this little trick of multiplying it by the perfect version of 1, and then that leads you within a few steps to this thing. And now we're almost done, except that I still have an answer in terms of theta, and the original question was in terms of the variable x, so I still have to use this to re-express my statement in terms of x. So I gotta go back up here, let's go back up here, and I want to find a way to restate ln of the absolute value of secant theta plus tangent of theta, absolute value, plus a constant. Right? That's this guy. Okay, well, we have that x is equal to a secant of theta. So x over a is equal to secant of theta. And if we create a triangle now, here's my theta. So cosine is normally adjacent over hypotenuse. Adjacent over hypotenuse. So this secant is going to be hypotenuse over adjacent. So this is going to be x over a. Good, good, good. Okay, and there's some value over here missing. And if we use the fact that a squared plus b squared equals to x squared, we get that b squared is equal to x squared minus a squared, or that b is equal to the square root of x squared minus a squared. That's exactly what this is going to be. The square root of x squared minus a squared. Okay, so now we have everything we need to restate this in terms of x. So secant, as we said, well, that's just x over a. And tangent is going to be opposite over adjacent. So we have everything we need to re-express this as ln of absolute value of, and then we have x over a plus square root of x squared minus a squared all over a, plus some constant. So at this stage we could stop there, but often we see this simplified a little bit more. Since both of these fractions have the same denominator, then we can simplify it this way and say that this is x square root of x squared minus a squared all over a, absolute value, plus c. And because we have a giant fraction here, remember that one of the properties of the ln is that, here I'll put it in green, remember that if we have ln of a divided by b, this is equal to ln of a minus ln of b. Right? So we can just subtract these. So this becomes ln of x plus the square root of x squared minus a squared minus ln of a minus c. And then whatever this is, a is some constant, right? So it's not a variable, it's just some number, some value. So we can just combine these two constants to be some c constant, I don't know, c star. Good. And so I can rewrite this as ln absolute value of x plus the square root of x squared minus a squared, absolute values, plus some c star, some constant that goes in the end there. Okay, so this would be a perfectly good answer. Or if you look it up somewhere, most often they do that. Okay, let's see if I can zoom out and get a nice little shot of the whole thing. Just barely. Cool. All right. So let's see if the author agrees with me. Did I do it right? Let's see. So we strict our theta to be between 0 and pi over 2 and pi and 3 pi over 2. Good. So we plug it in there. That simplifies the same thing. A tangent of theta. Plug it into here. That also reduces to secant. Okay, looks like the author just assumed that people knew that and just jumped to that. That's fine. And then you use your triangle, create a triangle, same thing, and you end up with this, which simplifies to that, which then, if we let c equal to that, we can just say it's some c sub 1. Instead of c star, you can put c sub 1. And hopefully mine matches with the author's. ln of x, and then x minus a, and then x plus x squared minus a squared. Okay. Cool. All right, last example.
Example number 6. Find the integral from 0 to 3 root 3 over 2 of this ugly thing. Okay. So, first thing we want to do is play with this guy a little bit, the denominator. So let's play with this over here. If we have 4x squared plus 9, and the whole thing is raised to the power of 3 over 2, that's really the same thing as saying that this is equal to 4x squared plus 9 square rooted, and then the whole thing is being raised to the power of 3, which is almost like something that we work with, except that we don't have a variable squared, we have 4x squared. So if we just manipulate this just a little bit and think of that as a little unit there, that equals that, plus 9, square that whole thing, and then the whole thing gets raised to the power of 3. So now it'll look, where's this? Now it looks a lot more like something we've been working with, where this is the variable, right? So if I had, let this be a w. If I had w squared plus 9 square rooted, if I had this, then as per suggested, this would be a case where we let the w equal to 3 tangent of theta, right? That's the thing that would make this work. Then we'd factor out the 9 and we'd end up with tangent squared plus 1. So things would work out nicely. So instead of a simple w, though, we have a 2x. So that's what we're going to do. That's our suggestion for this guy over here. We're going to let 2x equal to 3 tangent of theta, which means that x equals to 3 over 2 tangent of theta. And when I take the derivative, dx d theta, that's going to be equal to 3 over 2 secant squared theta. So dx equals to 3 over 2 secant squared theta d theta. So I have my dx. And I have the x that go right into there to raise it to a power of 3. Let's keep going over here so that we can figure out how to simplify this. So if I let the 2x equal to 3 tangent of theta, so let's just go from here. So I had 2x is equal to 3 tangent of theta. So this part here gets replaced by 3 tangent of theta. That's the 2x, right? 2x. That whole thing gets squared, plus 9. That's inside a root, which is inside of something being raised to a power of 3. And then this gives you a 9 tangent of theta squared plus 9. Square root of that whole thing gets raised to the power of 3. We can factor out a 9, we end up with 3, and then the square root of tangent squared theta plus 1. That whole thing is still getting cubed. Good. And then this becomes secant squared. So we get 3 secant squared theta, and then the whole thing gets cubed. So we end up with 27. 3 times 3 times 3 is 27. And then secant cubed of theta. So the secant squared square rooted just becomes secant of theta, but then that whole thing gets raised to the power of 3. So finally we have all the components we need to restate this part of it. So let's leave the limits of integration alone for a little bit. So these are all expressed in terms of x. So this is x goes from 0 to x goes to 3 root 3 over 2. Good. Now the numerator is going to have 3 over 2 tangent of theta, and then that whole thing gets raised to the power of 3. Right? That's this x going right in there, being cubed, divided by, and now this whole denominator, well, we did a lot of work over here to get it to be 27 secant cubed theta times, so we have that, and now the dx is this part, which will be equal to 3 over 2 secant squared theta d theta. Good. So let's simplify that a little bit. And again, I'm leaving the limits of integration alone for now. I got to come back to it. I got to circle back to it. So x goes from 0, x goes to 3 root 3 over 2. We'll come back and visit that after I finish simplifying this a little bit. Okay, so this turns into 3 cubed is going to be 27 over 8 times tangent of cubed theta. That takes care of that part, times 3 over 2 secant squared theta d theta. And then again in this denominator we still have a 27 secant cubed theta. Okay, so 2 of those canceled out with 2 down there. There's still 1 secant theta remaining in the denominator. And then let's take out those constants. So let's just put the constants out here. I end up with 27 over 8 times 3 over 2 times, and then this becomes 1 over 27. Right? Pulling that out there. And so this 27 cancels with that 27, and I end up with 3 over 16. So this whole thing will then become 3 over 16, and that takes care of all these constants. So now I've eliminated all those. I took care of those. And I end up with a giant integral that has a tangent cubed in the numerator and a secant theta in the denominator. Integral of tangent cubed theta divided by secant of theta d theta. And I still have to deal with the fact that the limits of integration haven't been changed. 3 root 3 over 3. Good. Okay, so how to simplify this? Let's convert everything into sines and cosines. So this will give me sine cubed theta over cosine cubed theta. Right, that's tangent cubed theta. And then secant of theta is 1 over cosine of theta, like this, d theta. Integral as x goes from 0, x goes to 3 root 3 over 3, and there's still this 3 over 16 chasing us out here. And now the numerator times the reciprocal of the denominator is going to end up canceling one of those cosines. So this will reduce into 3 over 16 integral as x goes from 0, x goes to 3 root 3 over 3, sine cubed theta cosine cubed theta times cosine theta d theta, which means that this guy cancels with one of those and I have a little squared guy there. Good. Let's deal with these limits of integration now. So let's see, when x equals to 3 root 3 over 3, remember that our description of x, way up here, here it is, x is 3 over 2 tangent of theta. X is 3 over 2 tangent of theta. Okay, so when x equals to this, we end up with, wait, 3 over 3? I thought it was 3 over 2. Yeah, 3 over 2. Whoops. This should be 3 over 2. This should be 3 over 2. So 3 over 2. Okay, so when x equals to 3 root 3 over 2, that's the x, and it's got to be equal to 3 over 2 tangent of theta. right? It must mean, right, if we multiply both sides by 2/3, this cancels with this. 2/3, this cancels with this. So that must mean that root 3 must be tangent of theta. And that's one of our standard triangles, right? Think about the standard triangle of pi over 3, which is 60 degrees. Let's go that way. I think most people memorize it in terms of degrees. So this would be 60 degrees, this would be 30 degrees, this is 2, this is 1, this is root 3. Okay, so this is pi over 3, and this is pi over 6. And tangent is opposite over adjacent, so root 3 is 60 degrees. So this must mean that in degrees, theta must be 60 degrees. But sticking to radians, it must be pi over 3. Good. Okay, so we've established that this must go to pi over 3. What about when x is 0? When x is 0, we end up with 0 equals to 3 over 2 tangent of theta, which means that tangent of theta must be 0, therefore theta must be 0. Good. Good. Okay, so now we have our limits of integration. When x is 0, this is going to translate into theta being 0. And when x is 3 root 3 over 2, that must translate into theta being pi over 3. Good. Okay, so now we got everything we need to restate our integral, including the limits of integration in terms of theta. So let's zoom out a little bit and let's get out of this whole mess and let's put it right over here. So let me recopy it. 3/16 integral as x goes from 0, x goes to 3 root 3 over 2 of, and then we ended up with sine cubed theta over cosine squared theta d theta after I canceled out one of the cosines. Okay, but now we have new limits of integration. Also, I want to separate one of these signs and rewrite it as sine squared theta over cosine squared theta. And then there's an extra sine of theta d theta over there. And now I have that theta goes from 0 and theta goes to pi over 3. Pi over 3. There's still this 3/16 out here. Okay, so now we're going to do a u substitution. Nice classic u substitution, and we're going to replace the sine squared theta with 1 minus cosine squared theta over cosine squared theta, sine of theta d theta, integral from 0 to pi over 3, and still we have this 3/16 chasing us out there. So if we let u equal to, and there's nothing special about u, how about if we make it w? Let w equal to cosine of theta, then dw over d theta is going to be equal to the derivative of cosine, which is negative sine of theta, or dw, almost done, dw is equal to negative sine of theta d theta. So this is almost going to be my dw, but I do need a little minus right in here. Go away. Which means I have to balance it out with a little minus out there. So now this whole thing here will be my dw. And I'll have 1 minus w squared over w squared times dw. And then, okay, well, we can again convert our thetas. Right, so this is theta goes from 0 to theta goes to pi over 3. Okay, so when theta equals to 0, w equals to cosine of 0, which means w equals to 1. That was easy. When theta goes to pi over 3, then w equals to cosine of pi over 3. which, well, that's 60 degrees. Cosine of 60 degrees is equal to 1/2. W equals to 1/2. Okay, so now we have everything we need to restate this now in terms of the variable w. So this will be equal to -3/16 integral as w goes from 1, right? When theta was 0, then w is equal to 1. And when theta is pi over 3, w equals to 1/2. So be careful with those guys, to 1/2. And then we end up with 1 minus w squared over w squared dw. Good, 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 good. Almost there. Almost there. This thing is getting really ugly. -3/16, and then this becomes integral from 1 to 1/2. And then this reduces to 1 over w squared minus 1 dw. Almost there. So this becomes -3/16. Then this is going to be ln of, oops, not ln of, this is just going to be -1 over, this is going to be -1 over w minus w evaluated as w goes from 1 to 1/2. Good, good, good. Okay, let's see here. So this then becomes -3/16, and then we have -1 over 1/2 minus 1/2. So that's evaluating everything with the 1/2 minus, and now evaluating everything with the 1 in there. We end up with -1 over 1 minus 1. Make sure that this thing is in its proper parentheses. Okay, so evaluating these two with a 1/2 minus evaluating these two with a 1. And let's see, we end up with -3/16. And we end up with, this is going to be a -2. Numerator times the reciprocal denominator become -2 minus 1/2 minus, well, there's going to be 1. Minus 1 minus 1. So minus 1 minus 1. Like that. So then this becomes -2. And then minus 2 becomes +2. -3/16 minus 2 minus 1/2 +2, which means that these two will cancel, -2 +2, so we just end up with -1/2, which ends up being -3/16 times -1/2, which becomes positive 3/32. Whew, that was messy. Okay, I can't even capture the whole thing in one screenshot. Let's see. A little bit. Not really. Okay, so let's just start at the beginning. Quick little summary. We start off with this guy. We made a proper substitution of that brought us to this integral once we made all the appropriate substitutions for the dx and the numerator. I kept the limits of integration up to there, but then I made sure to rewrite it as x equals so that I don't lose them. Simplified, cancel, reduced. Eventually, we had to figure out what those limits of integration were. So that's when I did this over here to change the limits of integration. and then I got something that was easier to express in terms of theta, but then we had to do one more substitution in order to find this integral, and I let w be my substitution. Okay, so then I rewrote that. I had to once again find the limits of integration for w, and so I restated my whole thing back in terms of w here, and then I was able to find my value there. Let's see if the author matches, and maybe theirs just looks a little neater than mine. Okay, so we're going to let x equal to 2x equal to 3. Where am I at? Here, x equal to 2/3 tangent of theta. Its derivative is 2/3 secant squared theta. Okay, so then you simplify that part of it to be equal to 3 secant theta. Plug it into the denominator, we get this. Plug in your x value, we get that. Good, so that's exactly what I did. Leaving the limits. Okay, so then we change the limits. We get the same limits of integration that I got. Okay, that simplifies to this. You can push out one of the signs. Sine squared turns into that. Good, we do another substitution. Good, they did u instead of w. I did a w substitution, which turns into this. Okay, they did a little trick here where we were able to flip this around and rewrite it with this minus here. Okay, so end up with the same answer at the end of the day. Okay, that's good enough for this section. We'll stop here.